Hello everyone, I'm glad to meet you on 5th International Conference of Sustainable Futures, Environmental, Technological, Social and Economics Matters. My name is Ivan Sakhno. I am one of authors of paper Research of Influence of Stress-Strain Evolution in Immediate Flow Before and After Excavation Phase on Region Floor Heave in Coal Mines Roadway. If you will have any questions, you can send them on email to me. This paper is divided on 5 parts. The first one is introduction, the second one is engineering background, and the third one is methods. The next one is result and discussion, and the last is conclusions. So introduction is the first part. The post-war reconstruction of Ukraine will require a powerful energy and metallurgical growth. Therefore, it is most likely that the roadmap for the transformation of the Ukrainian coal industry will be adjusted at least in the near future. In order to ensure the rhythmic operation of coal mines, it is necessary to solve the issues of mine roadways stability. The floor heave is one of the most acute issues of underground mine roadway stability problem. About 17–18% of mine roadways in Ukraine are repaired due to dramatic floor heave. Slide 3 shows case of dramatic floor heave in coal mines of Donbas. The current method of excavation and supporting of mine roadway in Ukrainian usually do not provide floor support system to control the floor deformation. Many scholars have conducted extensive research of the floor heave. The main floor heave mechanisms are bearing capacity failure, buckling, and swelling. Usually, the stress-strain field in surrounding rocks in the cross-section of mine roadway is analyzed. At the same time, the change in the stress field immediately after equilibrium state, after before and after excavation is not taken into account. In this paper, stress and strain evolution in immediate flow before and after excavation phase was studied. This study provides a characteristic of the underground roadway excavation influence of stress-strain state of immediate flow and its delamination. The key study mines are located in Pokrovsky and Dobropilsky district of Donetsk region. The analysis of geological maps and the current state of the coal industry shows that mines in Pokrovsky and Dobropilsky district are the most perspective for the development of coal mining. In the current balance of coal production in Ukraine, 65% is the production of the coal by mines of DTEK company that was located in Western Donbas and Dobropilsky district. 23% is the production of Pokrovsky Gallery, Pokrovsky district, and only 8% of coal production is provided by mines located in the state ownership. The average unique self-compressive strengths indicators of rocks for mines of Pokrovsky and Dobropilsky district are presented in the table. The typical strata histogram are shown in slide. Okay, in the next part is the method. The 3D numerical simulation from NC Scott was performed to analyze the stress-strain distribution in surrounding rocks before and after excavation phase. To simulate the behavior of rock mass, the Drucker-Prager model was used. The numerical model is shown in slide. The model is axisymmetric, so half of the cross-section of the mine roadway was simulated. The model was 60-meter long, 60-meter wide, and 100-meter height. An arc-shaped roadway was modeled. A vertical pressure that equivalent to overburden stress in the 900-meter depth was applied off the top of the model. Mechanical parameters of rock mass are presented in the table on this slide. Distribution of minimal principal stress is shown in slide 9. A quantitative assessment of stress variation was obtained by analyzing of stress graphs along profile lines in immediate flow. On the right part of slide, the graph of the minimum principal stress variation is shown. The graphs of the build along a profile lines oriented in immediate flow, 0.25 meter below the bottom, along the roadway axis. The profile line is marked with dots. The following conclusions were obtained after analyzing the stress graph. At a distance more than 8 meters before the excavation phase, the stress field corresponds to the overburden stress, approximately 23 megapascal. The phase influence zone begin in distance of 8.0 meter before it. The stress increase from 23 to 37 megapascal, which correspond to its increase of 56%. The stress relief zone in roadway bottom appears immediately under the excavation phase. The stress decreased rapidly. At a distance of 2 meters behind the excavation phase, at a depth 0.25 meter in immediate flow, the stress are 3.8 megapascal. Therefore, stress reduce rate is 84% relative to the initial stress field and 19% relative to maximum stress concentration. Thus, the rocks in immediate flow are loaded cyclically. At the same time, the sign of the loading, unloading stress changes. After that, 4 profile lines were built to analyze stress-strain variation in the depths on immediate flow. Profile lines were oriented in the immediate flow along the axis of the distance 0.25, 0.5, 0.75, and 1 meter from the roadway bottom. The analysis of the minimal principal stress variation shows that the stress concentration zone before excavation phase in the immediate floor is limited by a depth of 1 meter. Slide shows also graphs on the equilibrium. Slide shows also the graphs of the equivalent strain variation. Graph shows change in the deformation type, compression, tension in the immediate floor before and after excavation phase. Thus, it was established that in the immediate floor in the influence zone of excavation phase, at the initial state of the roadway life cycle, compressive stress first increased more than 40% in the stress concentration zone. After that, they decrease more than 80% in the stress relief zone. In this case, the rocks undergo cyclic loading and alternating strengths. It is known that cyclic loading of rock leads to significant decrease of their strength even after the first loading cycle. Many scholars reported that cyclic disturbance results to numerous tensile crack and crack branching. So, in immediate flow behind the excavation phase in the stress relief zone, cracks are formed in the flow strata and existing structural defects are branched, interlayer contact are opened, and delamination occurs. This creates a negative impact of the roadway stability in the next life period. The fractures of rock can be prevented by artificially restraining the delamination of the immediate flow after excavation phase. Rock bolts installed with the inclination to roadway phase were proposed. The rock will be reinforced in the stress concentration zone, and their subsequent elimination in the stress relief zone will be controlled by the rock bolts. The rock bolt's inclination is advisable to determine from the stress pattern in immediate flow. The example of determining the bolt inclination by a graphical method for the simulated result presented above is shown in the left part of the slide. The proposed flow support scheme is presented in the right part of slide. Finally, the last part is the conclusions. It was shown that an immediate flow before roadway excavation phase, a zone of increased stress is formed. Maximal compressive stress in this zone increased by logical stress by more than 50%. The stress relief zone in immediate flow after excavation phase appears. The stress is less than lithological stress and maximum stress by more than 80% and 19% respectively. Thus, the rocks in immediate flow are loaded cyclically. This is confirmed by alternating strains in the area of phase excavation impact. Rock bolt support of roadway floor was proposed for restraining the delamination of the immediate floor after excavation phase. In this case, bolt installation in the timely manner in the excavation phase with inclination to roadway phase was proposed. The most appropriate bolt inclination coincides with the contour of the stress concentration zone. This is the end of my presentation. Thank you for watching and listening. I am waiting for your questions.